This is a 2D representation of an array of vertical lines. The core challenge here is to pick exactly two of these lines to form a container that holds the absolute maximum volume of water. To figure out how much water any potential container holds, we first measure its width. That's just the horizontal distance between the two chosen lines across the x-axis. But the height of the container is strictly constrained. If we try to fill the water past the shorter of our two lines, it simply spills right over the edge. That physical constraint gives us a concrete mathematical formula. The total area is the width multiplied by the minimum height of the left or right line. The most obvious way to find the maximum volume is to test every single possibility. We take the first line and pair it with every other line. Then move to the second line and repeat the process, calculating permutations with a nested loop. For an array of 100,000 lines, checking every pair requires 10 billion operations. That triggers automatic time limit exceeded errors on most coding platforms. We need a single-pass strategy. We solve this with a two-pointer approach. We lock our left pointer at index 0 and our right pointer at the final index to establish a baseline area using the absolute widest possible container. To search for a larger area, we have to shrink the width by moving one of the pointers inward. Because moving inward guarantees a loss of width, we have to mathematically justify which pointer to abandon. Let's test the natural instinct of saving the tallest line. Look at this state. Our left pointer is at a height of 3, and the right pointer is at a height of 6. If we move the taller line inward, we might find an even taller line, say height 12. But despite this, the area strictly decreased. The width shrank, and the total water height is still completely bottlenecked by the unchanged 3-unit line on the left. If we shift that taller line again and hit a much shorter line, the container's volume drops aggressively to match this new, lower bottleneck. Shifting a taller line guarantees the area will either shrink or stagnate. To overcome the loss of width, the only logical move is to discard the shorter line and hunt for a new, higher boundary. Now look at this board state. Our left pointer is at height 8, our right pointer is at height 4, and our maximum recorded area is 49. Pause the video and determine the next logical move. Right now, this container has a width of 6 and a height limited to 4, giving us an area of 24. Because the right pointer's height of 4 is the current bottleneck, it must shift inward to seek a better height. This process simply repeats. We calculate the volume, update the maximum area, and step the shorter pointer inward until the left and right pointers meet in the middle. Translating that logic directly into code gives us a standard while loop that runs exactly as long as the left pointer is strictly less than the right pointer. Because the pointers never cross, we process the data in a linear, single-pass sweep. This chart compares the massive operational mountain of the nested loop against the flat, highly efficient line of our optimized single pass. To solve this effectively, follow 3 rules. First, always calculate the area based on the shorter height. Second, continually update the maximum area found so far. And third, always move the pointer attached to the smaller line inward. By proving the taller line is mathematically irrelevant to area growth, we eliminated 10 billion wasted operations, solving the problem in a single sweep.